this is a finals week, and I think many students have exam, but it's good that quite several of you showed up. So we have Josef Sivic from India and Paris. He's well-known researcher in computer vision, got his PhD from Oxford University under Andrew Zisserman, and he did a postdoc at MIT for a few months. Then he has been there in India since then, and he's going to talk about his recent work in using neural network and so on, deep learning.
Thank you. Thank you, Mubarak. Thank you very much. It's really great to be here. So I'll talk about our recent work on learning mid-level image representation for visual recognition. And I will start just by asking why is visual recognition important? So visual data is all around us, from archive of visual information store, internet videos, TV channels, or historical imagery. And cameras are all around us, from surveillance, car cameras, even personal cameras. And we would like to understand, organize, and search all this visual data. And so I'm just going to mention 3 applications which I particularly like. The first one is automatic search of visual archives. So imagine you could automatically search all the historical imagery which is stored in archives all over the world, and then find, for example, all images of a particular place, how it evolves over time. So this is the Notre Dame Cathedral in Paris. And so when I put this slide together, I noticed that actually there are some buildings which disappeared over time. So imagine you can study this for applications in archaeology, architecture, or urban planning. So the second one is, second application I like is intelligent visual memory. So imagine you could search automatically all your personal photos, either on your mobile phone, or if you run with a wearable camera, or your sort of visual memory, so things which you see, asking questions like, when did I see this person last time? The third sort of application domain which I like is the perception for interaction. So imagine you want to build a robot which will interact with people. You might want to understand what people are doing and their actions. So this is mentioned these 3 applications. And in this, so these are sort of broadly my research themes, which are instance node recognition, learning models for category level recognition, and recognizing activities in videos. And in this talk, I will really focus on just recent papers in the first 2 domains. So I'm going to talk a bit more in detail about this, and I will not talk about recognizing people in videos. So I just thought to show on one slide because I know that lots of people are interested in this domain. Here also, so we've done back in Paris also work on recognizing people and what they do in video, and using also sort of more detailed representation like segmentation, pose estimation, and interaction with objects. And just as an example, you may have seen in ICC last year in December in Sydney, recent work of Piotr Bojanowski on where the input is videos with scripts, and the method learns the appearance, face appearance of different people, and also different action recognizers. So the output is a location or localization of the person, their face, and also what they do. So the hillside walking. So this way we can associate names to individual people and also recognize the action of an individual person. So that was just one slide on video, but in the talk I will focus on these 2 domains, and I will start with representations for instance level visual search. And by the way, if you have any questions, just ask. So if you want to understand something, just ask. So here the goal is given, so a query image like this of an object or a building, you like to search a large collection of images to find the same object or building despite changes in viewpoint or illumination, or even if you want to find some archival depiction of that place. So why is this difficult? as I said, we want to find the same building with 5 changes in viewpoint, illumination, partial occluded by the trees, and also when this turns out to be a major difficulty, changes over time, like buildings being destroyed, and then this should start. We have a same building in the archive as a, say, engraving or a painting. So I also start a little bit with the history, how we approached this problem. So we were inspired by searching text, which is very efficient, high precision, scalable, but we needed a visual analogy of a word. So we obtained that by vector quantizing the appearance of local invariant features, which as a result, so even say part of the object, even if it's small or big, or they take different viewpoints, they get to map the same called visual word in the quantized appearance space. So this is kind of a pipeline. We detect local regions, normalize, compute a descriptor, typical SIV, and then find the nearest cluster, which would be given over Z out of some vocabulary of V visual words, and this mapping is F. And I will come back to this notation that I'm going through with more detail. So we map the input descriptor X into some vocabulary Z by this mapping map. And here is an example. What you can do is to find the query building in a large collection of 1,000 images, even if it's under changing viewpoint, and the green links show the matches between the individual local features. And so this kind of representation approach has been quite successful and used in many different areas, and it has been improved over the time by different aggregation methods like Fisher methods or blood descriptor, and used for many applications, like place recognition, for example. Some very nice work coming in this domain from here also. And what I'm showing here, it's also applications mobile visual search. If you have a phone in your pocket, it's probably, you can use the Google goggles and search for book covers, planar objects, textured. They work very well using this type of local feature representation. So this is great. So we can now take this approach and then apply it in search, or try to search the archives of historical imagery and help the historians or archaeologists to find all these images they want. So this is great. We can try that, but it turns out it doesn't work. So if you do this, if you apply the same type of technology which you see, so this is an example which Brian Russell did. So this is a painting. And this is a historical painting, watercolor of this site in this house in Pompeii. This is a recent photograph, and if you try to match those using sort of shift-right regions, you will get zero correspondences. Why? Because although this is imaged by the artist in some realistic manner, still it's a non-physical manner. So the appearance, the shading is not a photograph, and also there are structural changes like part of the column missing, the texture is completely different. Here there are some stripes which are missing. So we'll have to do something different to address this difficult matching problem. We are not the first one to note this. Here is an example from a paper by Shrivastava et al. Who tried to match scenes across large changes in illumination and others. So local features struggle to match images across large changes in appearance. So the approach we've taken was to actually use 3D model to help the matching. And so this is a paper which is just came out in the talk, and really the credit goes to Matthew and Brian Russell who did the work. So here the idea is that we are given a little painting and a 3D model of the same site, and we'd like to match the non-photographic depiction to the 3D model. And we will assume that approximately the painting is to the first order perspective projection. So we will try to recover approximately the camera position of the painting with respect to the 3D model. And here is an example of an input painting. This is the 3D model aligned with the painting. So of course we are not the first ones to use the 3D model for recognition. There is this very nice work by David Lowe and so many others, this is recognition by alignment, which typically relies on extracting object contours from the images. But it turns out that extracting object contours from these non-photographic depictions or in general cluttered photographs is very difficult. And extracting contours from noisy 3D models like this one is also hard. So this is an example of our work from 2011, and we tried it, and we found that actually extracting contours is not easy.
So how do you get a 3D model for this?
Yeah, so very good question. So this model and this one we are built using large-scale multi stereo methods from University of Washington. But I will show results also using simplified CAD models later. So both are possible. The real ones are noisy on the edges. It's basically harder. So the second type of approach is using matching using a global descriptor, which could be like for example the GIS descriptor, which has been used to some success for this task, but it also has problems. It struggles to really match across the large changes in viewport because it's a single global representation. So instead, what we're going to do is to build on the recently developed methods in for category level recognition, which represent objects or scenes using a large vocabulary of what's called mid-level visual elements. So these are so this is a vocabulary which is large, learned specifically for certain tasks, which can be recognizing particular city or object or even action and video. And also it's not local, it's sort of this mid-size. So we'll use that and we'll ask the question, what is the right visual vocabulary for matching the paintings to the 3D model? And so now I'm going to go into details how we are, how we do this, the matching, how we learn the vocabulary, how we match the 3D model from painting to the 3D model. And you can see it's difficult, so so the 3D model has the same building as depicted here, but so matching those with such a large changing viewpoint is hard. So how are we going to do that? So the first thing what we are going to do is to synthesize different views out of the 3D model. And these different dots are showing locations of the virtual cameras we put on the site. So we synthesize about 10,000 views for this model of Venice. And the outcome of this is that you don't have to match the painting across large change in appearance, because we will have one of the views which is approximately from the similar viewpoint. So the matching problem now becomes much easier. But of course we have to find the right matching. Second, so how we will cast the matching as discriminative classification. So here I'm giving you a rectangle, so this is at the moment specified by hand, and we represent this patch of the image, query region Q with a Hop descriptor. So this is showing, I guess you're all familiar with the Hop descriptor, which captures the orientation of the image gradient. But what it does, it captures the object boundaries in this soft manner. You don't have to make hard decisions. Where is the object boundary on the 3D model? And of course, this is so this is just an example of trying to extract the noisy boundaries from the 3D model directly, and so which is difficult because all this noise on the model. And so the next step, what we're going to do, we're going to train a linear classifier in this form where the parameters are W and beta, with having this query region as a positive example, Q and a large number of negative examples. Usually patches from some negative photos, from generally other photographs. So this is related to the exemplar SDM training, but here what we do not for object detection, but for matching. We train that classifier for that specific query region, which we will be matching to the painting. And here are the example of the ways which we learn. So these are split into positive and negative parts. You can now see the different arches, the bigger one and the smaller one in the category. Yes.
On the left side, the 3D model, you could have had different lighting and conditions and so on. You sample with a different height?
So at the moment, it's a very good question also. One can imagine to vary other parameters in the rendering, because we in some sense synthesizing training data than just the viewpoint. So we did a little bit, not in illumination, we did in the paper a small study on changing the style. You can imagine rendering this, so trying to emulate a certain style, like a drawing or a watercolor. So we did try a little bit of that. And the experiment was quite small, but the initial results suggested that, and I think for one of the depiction style, I think it was drawing, but I'm not completely sure, it actually helped improve the result on matching to the drawings. But on the other depictions, the results decreased, so I think one would have to somehow work more at it, maybe recognize the style. But I think it's a very good idea to try to synthesize other variables in the rendering. Yes?
About the query region, you mean in the 3D model?
Yes, well, so this is the region in the synthesized view. I will show later how we so we do this for every synthesized view, actually. So I will show next how we choose this region. But at the moment, it's a region in the synthesized view of the 3D model.
So it's an image, actually.
So this is a synthesized image, and you see the pixels here. And here at the moment, I choose the region by hand. And of course, the next question is, how do I choose this region? Do I try all of them? How do I choose this region from all these 10,000 synthesized views? Before, I'm just going to explain it right now in the next slide, but just before I do this, so how we then do the matching, once we have the region, we learn the classifier in this linear classifier, this form, and then to detect this patch, this region in data, because scan densely, like the sliding window manner, the classifier as you would do in detecting object and find the best match.
So this classifier, how do you get you get lots of examples for this classifier, or just one example?
So at the moment it's a one example, one query region, and lots of negative data.
Oh, I see.
So imagine the intuition is that it's learning is kind of the most discriminative projection or dimensions of this point with respect to the negative training data.
But you could have just used just compare the actual descriptor directly.
We could have
Just compare the actual descriptor from this region.
we could have, but the idea is that actually, so Matthew has evaluated, I will show it later in the different variants, doing this learning classifier works is good.
So how do you choose this particular view, or how to code? You have to train several classifiers for different positions on the...
Well, so how do we do that? How do we choose the query regions? And so it's right. So there's a question: how do we choose which query regions we use? And for this, we will look at the cost function. So what is the cost function when we train the classifier? So it has this form where we have first the query region Q, the hot descriptor is labeled +1, and also negative descriptor is labeled -1. And here is the cost, so it's a loss on the positive example and some losses on the negative example. So, and there is ignoring the regularizer. So you see that it would be a cost for an SVM support vector machine, which I guess some of you have seen before. And this would be if you use hinge loss for the loss on the example. Instead, what we're going to do, we're going to use a square loss. So this is really just taking the predicted value compared to ground rules and take a square. So why is this beneficial? It turns out that if you use the square loss, and it's not something that we invented, this is so very well known thing, we can compute the W, the optimal classifier, and the parameters W and beta in a closed form. So given these positive and negative examples, we can just, instead of some expensive iterative training, and like we would do in learning SVM, we just compute WNV tangles. And of course, they are not even recently this form of square loss for classifiers has attracted attention because it has been shown that even if you want to train a pedestrian detector, actually using a square loss is not a sort of performance reasonably low. So we can compute W and beta, but we can also compute, and I'm not going to sort of explain these equations in detail, sort of showing them here, but imagine we can compute as a function of the training data, and then what is seen there is the variance, sigma of the training data, and the mean of the examples, here the equations. We can compute WMP and also the energy, the optimal, the loss for the optimal solution for the classifier. So why is this useful? Now what we can do, we can then, because it's fast, it's equals 4, for every single pixel in the image, you can compute the W and beta equals 4 and compute its, the loss of the energy, the cost function. So the intuition is that if a particular Q has a very large cost, then it's not very discriminative from the negative point. It's hard to discriminate. Whereas if it has low training costs, then it's very easy to discriminate it from the negative point. So we can show this as an image where I'm showing 1 over the training cost. So it's kind of a discriminability score where sort of low is low score, blue is low score, and red is high score. So the regions with high lots of red are highly discriminative. So they have low training costs. So what I can then do is to just run a non-max suppression and on this densely evaluated cost and obtain a set of most, you can think of it, most discriminative parts for the transition. Yes?
So based on this analysis, we can say that the patches that you have the high cost for or the low cost for are low discriminative compared to the negative results.
Yes.
And you cannot say that about other patches and other viewpoints in other videos, right?
Yes, so this is a very good question. So at the moment, these are the most discriminative compared to some generic negative data. And we use this generic negative data from this book. What we do have, and we could have, and we haven't tried to using the specific patches from the same site. What we do have, and I'm actually not going to talk about this much in detail, we also have a kind of a verification stage where we try to detect these regions enclosed by these. We know everything about the both sides. So we can just run this detector on enclosed by views and check, are we getting the same region? And we do this step also, I'm not going to talk about much in detail, but we do have it, but more like a cross-validation step. And we do this we can do this over multiple scale, and then we get these sort of set of most discriminative parts for the specific site. So what's the nice thing about this, you can think of this as a generalization of local feature detection. So if you know, like a Harris corner detector is going to look at a neighborhood and look at places which are sort of different from its local neighborhood corners. But here we are looking for places which are different from some generic set of images in the and using this cost function as a way of evaluating the spot.
So these are images which are synthesized from 3D models.
Yes. And it's all done. So what the approach, and I think it's coming. The summary is coming in 1 or 2 slides. So we do it for all synthesized views and find this vocabulary of elements, about several thousand, which summarize the entire site. Now, because we know everything about our synthesized world, what we can also do, we can take the page here and back project it, cast the ray. We know the camera position, the calibration. We can cast the ray back onto the 3D model and back project this patch for the 3D model. So we really, for each of these patches, we have the classifier, which appearance-based classifier, together with the position in 3D and its orientation.
So, I mean, since you are synthesizing the 3D and then you are basing your features on HOG, which are gradient permutation heavily depend on the intensity values, not much on the shape. Right? So, I mean, what's the reason, like you said, those kind of method where you find the edges and projection of 3D models for edges will not work as well. This will heavily depend on how you synthesize, and that's very different from purely image that are taken from the different dimension, lots of different things.
So it's a good question. So there are two things. First one, so in one of the slides I was showing, the key problematic step is not so much computing the gradient, but the thresholding value when you sort of want to decide at a local level if a particular pixel has an edge or not. So this turns out it's one gets very noisy contours. It's not easy to extract light or object properly. So the first thing is that the hog is capturing this structure of the edges in a certain quite potentially complex neighborhood or patch in this soft manner, not making the decision is there an edge or not, hard decision. So it's being used to train the classifier and then kind of waiting for the decision to make the decision later. So that's the first point. Second point is that because we train the classifier, we are looking at the kind of most discriminative parts of that. So the kind of edges are the important, the intuitions, the important contours will get emphasized in the W. So taking the descriptor to W. And there's a third part which I sort of didn't talk about much in detail. So what Max Logray did, he kind of hacked a bit the hog descriptor so that he can be applied on these synthesized views. And there are sort of several things. One of them is that in these low gradient areas you don't want to compute edges which you can amplify the JPEG artifact or something. And also, and this is going to be important more for the next part of the work when we match get models. We also has kind of a mask. What is a kind of segmentation of the object in the image. Okay, so here is the pipeline. So we have a 3D model. In the offline stage, we render views, find these discrete visual elements, filter elements unstable across viewpoint. That was the so this is called the cross-validation step, throwing away things or patches which are unstable with respect to local close-by views. And then at the best time, we obtain a depiction, apply all these object detectors classifiers on the depiction to find tentative correspondences, and then we recover the viewpoint.
So your 3D model is point-based or the polygon, or what's the 3D model?
So it's meshes, yeah, which have some texture. So typically the EMBS, which is multi-use caroda, would have some simple texture from the photographs. This is an example of a model from Google Warehouse, Google Warehouse now, which has some simple texture applied to it, which I guess was done by the person who created the model. So this is just showing an example where we run of correspondences where we apply all these elements onto the painting and then just run a ransack as we would do to recover the viewpoint of the painting with respect to the. So these are the correspondences consistent with that perspective projection. Yes.
Ms. R, as I understood you correctly, you basically use a 3D model to get your synthesized views, which maybe fit a little bit better to the requested query image. So is that correct?
So the main step for the synthesis is that we convert in this case, we convert the difficult problem where you have at the same time large changes in appearance and changing viewpoint to the problem where the viewpoint is similar. So in our set, you have some views which have similar viewpoint, and then the matching becomes much easier.
Because my question is, once you have your artificial or synthetic view, you perform some 2D-based or color-based feature extraction. But I assume that you use the color which somehow comes from your 3D model, and again comes from the images of the big database which has been used to reconstruct the model. So, but here in a certain way you are also like subject to all these artifacts like illumination changes. So do you use any advanced methods to get rid of to sort of free the color of all these artifacts?
So no, and so okay. So it's true that we have the models which are reconstructed from say Flickr, like this multi-view stereo. One could use because for some parts of the model which are photographed many times from the different illumination, one can use that information. At the same time, some models like this one, they are really simplified models constructed by people and downloaded from Google Warehouse. So there are no large databases of photographs behind this model. Someone just created this model in the Google Warehouse SketchUp application.
So the only post-processing, so you do not do any advanced post-processing of the color, maybe except aberration?
No. So experiments, so we have four models. The first one is the Venice, is PAES reconstructed photographs, and then there is 3 CAD models from the Google Warehouse. We have about 377 test queries split across different depiction styles, historical photographs, painting, drawings, engraving. I'll first show example visual results. So this is the gray historical photograph, and this is the defined matched view from the 3D model. Here is another example. We'll go quickly through those. Different size Notre Dame, paintings and drawings. So now it becomes interesting because really the appearance change is quite big of the painting with respect to the 3D model. Here is another example. Again, with a large change in appearance. One more example. So this is really our models with significant 3D structure. I like this example because it really shows the power of having part-based representation. So here you can still match this even despite the fact that there is significant occlusion by people in the land because of the object part. And one more example, again, significant change in depiction style. Some difficult examples when the appearance change is extreme. Some part of the model, especially for our large sites, may not be covered. Some part of the 3D world may not be covered by our model, or extreme geometric distortions. We can also recover, because we have the viewpoint, approximate viewpoint, we can depict the viewpoint with respect to this painting with respect to the 3D model. One more example. And we also quantitatively evaluated the matching. So we split the, we did it on a user study on Mechanical Turk, where we had 3 categories: good match, which means something like this; coarse match, where the viewpoint may be correct, not correct, but the correspondence is on both the view, matched view, and the query depiction depict these different parts of the scene and that matches. And here are some results for different methods. So split across these categories. So interestingly, we can sort of well localize about 51% of all these 337 queries, which is quite good. And sort of unique to the coarse match is about 70% of the query examples we can match correctly. What's interesting is that the best performing baseline is actually matching 6 descriptors on the rendered view. So the step of the rendering the view is actually an important one. So it helps the SIF descriptor too, because you really compensate for the difficult viewpoint changes. Now, by analyzing these numbers a bit further, we found that the very good performance is actually due to matching the historical photographs. So if you remove them from the set, the SIF matching drops significantly to only 27%. So matching using SIF for matching paintings, it's still difficult. So it's whereas our method is almost unaffected by different type of depiction style. We ran the method on the data set of Haugash and Snavely, which has these aligned pairs of images with large changes in appearance due to sometimes depiction style, but illumination also. And the method is really doing significantly better than the baseline and their method, and also a couple of baselines which we tried. And I will finish this part. I will finish this part with a video again showing the matches with respect to the 3D model of the different depictions. And again, the point is this is a simplified CAD model from the warehouse, not reconstructed from multiple stereo. And you can still match it even cross changes in scale and that. Yes.
I have one question. So how, like, you know the approximate location for the paintings, right? So how close is that?
So we know in this case, we don't know the actual, I would say, location. We know that these paintings are from that site. So we, at the moment, we're not matching across different sites in this case.
Okay.
So we would know for a painting it's of Notre Dame, we don't know where.
Okay. So like, it was like interesting that like Sivic was performing so well, and then there was like a global patch, and I see like a serious deformations between. But like I was wondering like what would happen if you had like a global kind of scene descriptor, like something like gist, because
so
maybe the patches would not be so similar, but the gist of the scene, it looks...
Yeah, so we tried that. I don't know if it was in this evaluation, but it was significantly worse. So you really you need the local parts to cope with it kind of allow more deformation even with respect to the viewpoint. I guess maybe you could ramp up the performance of the global descriptor by really sampling like much more views. But with the type of sampling which we have, which is already quite large, you really need it works much better. I'll show some comparison later for objects. It's really, having the parts helps a lot.
So could you walk to the last table that you have there?
Yes.
Not the next one.
This one next.
Yeah. So in this, if I do not run this data set, could have models that you don't have in 3D, right? So how did you do this comparison?
So at the moment, we really, so in some sense, this data gives you like two views which are aligned, so there is no synthesis step. It's just a matching evaluation of the matching power of the descriptor. But it's a good question. So in some sense, this is a simplified scenario coming from this paper where you already start with having two views which are roughly aligned.
So in this, you are evaluating HOG matching pretty much with Ransack is what you need?
Right, but no, so what we have used our discriminative classifiers to train so the method that you're using, so we compare with different ways of doing the matching, but it's really using the discriminative matching. It's really evaluating the discriminative matching.
Oh, okay.
Right, so I have to, I think, kind of speed up a little bit. So I will, I guess, skip some of these questions. And so now one question which we were thinking about, that we could match these 3D models to photographs, well, could we apply this to objects? So, and this is really kind of, maybe if we have objects of like a chair, maybe we can use the same method to recognize the chair in different photos. And that really sort of leads on to the second part of the talk, which I'll sort of speed up a bit. So here the goal is that we would like to give an image. We would like to first, well, maybe name what the object, or what objects are present in the image. Like a chair, flowers, clock, table. But you would like to also localize the object and not only provide the bounding box. We would also like to provide an approximate 3D model of the object, aligned with the image with the correct viewpoint. So knowing this is some kind of an antique chair. Again, this is hard. Objects like chairs, I'm going to be using chairs as the running example, are depicted in embedded in complex scenes and different viewpoints occluded by other objects and other chairs. Under difficult illumination. So as this is similar difficulties which you had in the previous work. Here, in addition, you have the difficulty of modeling the intra-class variation. So here, the chairs are sort of, famous for having a large intra-class variation, so we have to somehow model that. And typical way would be design some statistical model and learn the variability from data. So we will need some training data. And of course, so there's many different methods one can organize them. There is going to be amount of supervision they need. So you can just use unsupervised, no labels, just images to learn the variability in appearance from the data, or maybe just an object label, like there is a tiger present in this photo, you don't know where. Or you can have strong supervision, knowing bounding boxes, locations of the object, or maybe even locations of the parts. So in this work, I will try to show you two pieces of work quickly. Is we will use even more, we will use full 3D models as supervision. And at the end I will show that, well, maybe we can relax that and use some kind of a transfer learning method. So of course there's been lots of work on 3D object recognition, which I want to now localize chairs, these are 3D objects. Often they use some simplified 3D models, which say represent the object as the same frame part. So in our case, we'll use a different approach. We'll really use these detailed, somewhat detailed cut models and large collection of them. Again, this is a paper which is going to appear at 3D. So we have, so what we have is this large database of 3D cat models, which we downloaded from the Triple 3D warehouse. So you can just kind of share in the on the site, and it will return all these models, which one can then clean up to sort of just keep models of chairs. So we altogether collect about 1,400 3D cat models. So now the question is, can we represent the variability of the chair category using a set of examples, a set of instances? So here are a subset of those. So you get the variability of the style from modern to antique chairs, simple ones, or so forth. So what we're going to do, and it's going to be very similar to the approach I showed for matching the landmark, the 3D models of landmarks, but here done for chairs. So we're going to synthesize 64 views for each of the chairs. So we'll end up with this data set of almost 90,000 images. But for each chair, so we have sort of two labels for each image. One of them is the chair label. So we have about 1,400 models, and then for each model we set of reports. And we apply the same pipeline. So I'm not going to describe it in detail, but again, we'll try to find the most discriminative elements or desynthesized views using the same notion of the discriminability as you've seen before over multiple scales. So we end up with, for each chair, for each synthesized view, by this set of these classifiers. So we have altogether about 800,000 classifiers, which represent different parts of the chairs from different viewpoints. So we have this large vocabulary of these discriminative elements, where each element is this classifier, so they are identified by Z, and each element is a classifier, and which has these style and viewpoint labels, and also we record image position because we can form a particular view in form of a star model. So these are all learned from these synthesized views. One note, and I'm not going to explain this in much detail, so they are all learned independent of each element. So for this to work, and this relates to the question, how do we compare the responses across different chairs? So this is a question here before. So what's absolutely essential is to calibrate the different classifiers in respect to each other. And we do this using a large negative data set of patches. So you can think of it compared to, say, a deformable part-based model, which is learned jointly with small set of parts. We have very large vocabulary of parts which are learned independently and calibrated later on a common data set. So now what we can do, we can give an image, input image. We can run all the element detectors and again find the model here of the chair which has the highest score. It's a chair and the viewpoint for this image. And again using spatial consistency. Before it was using Brown's technique for camera. In this case it's a sort of a star-like deformable model. Here is another example, again input image, and these are the corresponding parts found by the method which I just described, and the links connect the corresponding parts. Again, the viewpoint and the star is something similar. Here is another example, but this chair is, you can see the star is something quite different. So here the legs are maybe similar, but the back of the chair is different. But still the method can match those together quite reliably. And here is another example of also a chair with a different star. Here are some more examples. Even some exotic chairs which we have kind of chair in the database. And here is a comparison with the deformable part-based model. So here are input images. This is output of the DPM, so it's the bounding box of the parts. And this is output of our method, and we show the 3D model overlay over here. So you can see that we are getting approximate position and orientation of the object in the image. And the last column shows the aligned models on a point of line.
So how do you find the pose? Because each page can come from different viewpoints.
Right, so at the moment, it's a very good question. In this one, we force all patches to come from the same viewpoint and the same chair. So this is really kind of taking all attributes and independently trying to make them today. So there is no mixing. But I will come back to this in a bit. So here, so what's important, you can see, for example, in the top image, the deformable model kind of struggles to localize the chair because it's unusual. So if I parts of the chair, our method actually it turns out we have a similar type of chair in the database and can match it to the image. Here is some comparison. So these are all, by the way, images from the Pascal 2012 validation data. So we have this data set, 179 images, all coming from validation data, which comes with the ground truth, and we can compute precision recall curve for different, comparing our method to the baselines. So the first, the black curve is the single template baseline. So there's a question, how important are the parts? So this is what happens if you don't have any parts on the object. Next, the red curve is our method, sort of vanilla, using the parts. The blue curve is the DPM, so you can see it does quite well. It doesn't have the recall quite because some of the unusual chairs are not fetched. And if you use a simple combination, just averaging the scores of our method and the DPM method, which works better than any of the two. So getting the precision and the recall of both. And here are numbers. We also evaluated on the quality of the match of the style and the viewpoint. It's in the final version of the paper, which is not, the numbers are not here. I think about 80% we get the orientation within 20 degrees is the number. And so what's interesting here is that, so there's a question, how many chairs do we need? And so initially we thought, well, maybe 1,400 chairs is a quite large number, but it turns out almost that there's no in the world, there are no two chairs which are identical. Available images, and these are the best matching chairs from our database. And you can see that, so some of them have similar, maybe bottom, but none of them has the exact number of the bars on the top. So this led to the idea, well, maybe some of them maybe have similar top but different bottom. So this led to the idea, well, maybe we can mix and match parts from different models. And this so led to kind of a new work which is in submission. So I'm not going to talk about in detail, just show you an example. So we have this model which can really now mix and match different parts and kind of explain the input image as a linear combination of, we can think of it as a basis of the different chair parts. So here is kind of visualization of the result. Now what is this useful for? And I imagine for each of these chair annotations, say in surface normals in the database, I can then use the matches to predict structural annotation like surface normals for the image. Here I think green is up, red is this direction, and blue is towards the color. I'm not going to talk about this in much detail. And I think, well, there's really not much time left, but what I want to do in the remaining few minutes is to at least give you a quick overview of another of our very recent work, where you can ask the question, well, do I really need for every object class to collect a large number of 3D models to be able to recognize it? Well, maybe you can sort of pre-learn part of the representation on some data when you have lots of training data, and then just sort of transfer it to the target task which you want to address. So this is what we're going to do here, and we're going to use representations based on convolutional neural networks. So this is a paper also going to appear at CER, and I want to just refer you, there is several other related works which are just coming up, which are listed here, and also lots of sort of convolutional networks have been around for a long time, so I'm just giving you some sort of these classic references, but there's been sort of renewed interest in that video recognition in the last couple of years. And so the idea is that we're going to learn representation, so referring effects on one data set, and we have lots of annotations, and then transfer to another task. And we're going to use representation on convolutional network architecture developed by Krzyzewski et al., published in 2012, which will obtain significantly better results on the data of that competition 2 years ago. So, and so credit for this work really goes to Maxime Kapp, who did all this. So here is just a review of the architecture of Krzyzewski. So given an input image, it's a sequence of these layers, some convolutional, fully connected, and output class label. And it's on ImageNet, so output 1,000 classes, like African elephant, wolf. So the parameters, so this thing has more than 60 million parameters, which are trained on 1 million labeled images. So these are all contain one object, nicely centered almost in the image most of the time, and with labels what is the object class. And its parameters of this network architecture are trained in 1 week on 1 GPU using stochastic gradient descent, using the constant operator function. So I'm not going to go into detail about convolutional networks. You can read this paper and more details. Now the idea here is that we're going to use some of these parameters which you learned from the ImageNet fully labeled data as an image representation, as a feature extractor, which we can then transfer to another task. So the challenge when we want to do this is that, so we are in particular going to be looking at the Pascal DOC images, is that the data sets may have different statistics. So the source data ImageNet contains mostly centered objects, not always, but mostly. Whereas in Pascal we may have multiple objects occluding each other in complex ways, and small objects embedded in complexity. So we have to deal with this. And second challenge is that the labels are different. So in Pascal there's one label dog, in ImageNet there are all these different types of dogs, but not a single dog label. So we have to learn how to map these labels to each other. So here just one slide overview of the approach. So we're going to use the architecture of efficiently pre-train it on ImageNet, classify 100,000 classes of centered images, of centered objects in the image, and transfer subset of these parameters onto, and you're going to do two things to deal with the challenge which I just described. The first one is you're going to have like a sliding window procedure, which is going to, well, really kind of able to localize them, so small objects in very complex scenes. And secondly, you're going to have two adaptation layers, which are going to learn how to adapt the output of this network, which will train 1,000 object classes of ImageNet to 21 classes of one size. And I'm just going to sort of stop here on the method, just jump directly to results. So here, this is Pascal 2007 object classification. The first row is the best performer in 2007, achieving this result overall. Second is the best published result on this data. And this is the result which Maxim got. So he did his master internship after, I think, about 2 months of work. One of the first results he got, just applying the strategy, was this number which significantly outperformed the best published result on this data. So this really kind of got us excited. And here are some of the results. So what happens, we are applying these classifiers in this sliding window manner. So we can then show like a heat map of the scores for the individual sub-windows and showing the probability of the object class. So we can really see that the network kind of knows where the objects are in the image. So here it can just about maybe 2 bicycles. So these are correct results. There are 2 birds here, both bottom here, and these are false positives. So here it thinks there's a bicycle. Some of the high-ranking false positives. So here, some more results. Again, sort of when we saw these maps, we were quite sort of surprised how sort of accurate in some sense, although we do not allow it on the localization or the classification, the network knows where the objects are in the image. So these are results on the Pascal 2012 for different variants. I'm not going to go into details. This is again the best published results on this data. And how it was, what we also found in sort of one sentence is that if you pre-train the network on images which are related to the target class, so say he really didn't do very well on horses, but he added hoofed animals from ImageNet, the performance increases. So if you pre-train network on the related classes, it works better. And we also tried it on action classification in still images where the classes are quite different, like jumping, foaming. Again, achieving the best results on this data. And surprisingly somewhat, again, the network kind of knows where these actions are happening in the image when it is too late for that. Right, so I will sort of very quickly go to some of the discussion. But what are the failure modes? One of the failure modes at the moment is occlusion. So if you have a chair which is, say, occluded here, the network doesn't see it. So this is particular for the CNN. And similar here. So one direction how do we deal with occlusions in this framework. Another more general point for discussion is that, so you saw kind of 2 very different approaches. In the first one, we had very explicitly, because we could synthesize, in some sense, the data with a very explicit reasoning about viewpoint and style of the object. Whereas in the other presentation, we had this very implicit architecture, which is completely learned from data, kind of a black box. So in the end, maybe the right approach would be somewhere in the middle. But so this is an open question. And the last point which I want to make is that at the moment, you should also think what would be the output of visual recognition systems, say. Is it like an object name which is in the image? For some tasks, maybe enough if you want to just search images. But here I have this example. Now imagine you want to interact with the world and you are a robot and someone asks you, please fold this chair. Maybe knowing there is somewhere in the images a chair is not enough. So for this, you may really need to have a more detailed representation of the image, knowing there is a full little chair in a specific position. This is the actual image here. So I think it's an interesting question to ask, well, what is the output of the recognition which you like to have? And I think one of the directions is maybe thinking about this other domain like NLP or robotics, what they would do. And I think I will finish here. Thank you very much for your attention.
Very good. So, Christian, so actually I'll ask you first question. So when you said you train an ImageNet, use those parameters for your Pascal problem. So what was the if you had trained on just Pascal, then it doesn't work that way.
Yeah, so I was there was some question at the beginning, so I was sliding over some of these. We had this evaluation, right? It's a very good question. So if you do train only on Pascal, pre-training, you get about 70.9 on this data. So you lose 11, so it doesn't break down completely, but you lose quite a bit of performance.
And these, on the ImageNet, they will train on the whole image, not on patches that you're doing?
So in the ImageNet, there is a little bit of jittering, what's called, so you use so the images are, I think, 250 and you use 220 crops, so there is a little bit of jittering in the position, but not much, there is not much strain.
But what does that mean? Like if you train on completely different data set, because there are lots of images that it is helping you, and if you train on Pascal data set, it doesn't, how do you explain the performance?
Right, so I mean, we can, so here really, so there is, it's one way to think about this overfitting. So we have, the network is 60 million parameters, so one really needs training data, it will label to learn all these parameters.
Yeah.
So one can think of these layers here as a feature extractor. So it's really if you look at and Rob Fergus has done very nice work here with Matt Saylor on trying to visualize the intermediate representation, and there are really these parts of objects coming out which are learned on the ImageNet data. So then when we apply this here, that the network is representing the input image in terms of what are these different parts present.
So these, you just use those parameters as they are, or you use them as a static find and you...
Yeah, that's a very good question. In this work for objects, we use them as they are, so really this is fixed. And these are these adaptation layers which are trained on data. In the actions we found that actually one can improve by sort of tuning or fine-tuning even the lower layers. So others, I think Rosgier, she has done very nice work recently also here in CPR. He found that actually adaptation helps even for objects. So I think this is still, there is, and I cannot believe that. So I think there is some improvement which we can still do by fine-tuning the parameters.
Any other question? Yeah, go ahead.
You said that this is a huge neural network and you have 1 billion images and 60 million parameters. So isn't then the neural network just sort of a database and this process of feeding one image into the database is nothing more than a comparison to the closest neighbors, something like this?
Yes, it's a good point. So first of all, you have 1 billion labeled images, it's true, but actually because of the jittering, so you show different shifts, the effective number is actually bigger than 60 million. First, second is you can train this network from more than 60 million images. You can train this network from more than 1,000 classes from ImageNet. Now, what is happening inside of the network? Will not speculate what's going on inside, but it's true that the network seems to have quite amazing capacity as a kind of a representation or classifier. What it can capture, as maybe you can think of a feature extractor. And if you look at the visualization that Fergus has done, it is quite interesting and how they are getting more complex higher up. At the same time, it does not lose efficiency. So applying this on a because of this hierarchical manner, you really at the bottom has only like 60 convolutions. So at the same time, so before we had, in the other board, we had 800,000 classifiers which had to be run independently for one class, which is very slow. Here you really get an efficient representation which seems to be super high capacity.
It seems that you can simply memorize all the images.
Well, you know, this, if you kind of look, you know, I don't know, generalize a bit if you look at the results of Zyler and Fergus.
Go ahead.
So in the first work that you explained the constructions, like the historical constructions, you were moving the camera in 2D, like in a plane.
Yes.
But in your second work, I guess you have to also consider 3D, right? So how many samples do you take for each of your 3D models that you have? How many different 3D?
So as was shown in the slide, so we use 2 pitch angles, and so altogether it's about 64 views. But it's a very good point that for the landmarks we had camera sampled on that plane, but I think we also had kind of 2 different pitch angles. But here we sort of do it around the object.
And how different parts, like if DPM can take care of the vulnerable parts, but how is this in your method, is it hard coded? Like,
so the I wanted to cover also things I didn't cover this in detail. So we have kind of a deformable model for each of these views, but it's a deformable model which has kind of a box cost for the deformation. So there's a set of allowable deformations which are a few pixels. So each part is allowed to move a little bit, but there is no cost as long as you stay within a certain deformation.
And how do you find the parts? Is it automatic?
It's the same way how we did it in the painting. So we evaluate this discriminative cost based on trading the classifier in a closed form. It's kind of, the method is very similar to the landmarks, except there is the calibration of the different elements, which turn out to be very important to calibrate the classifier.
So how important are those adaptation layers? I mean, did you try other classifiers like this SVM, just training an SVM, or how many number of layers shall you put over?
So here, so we tried a little bit of variation. We tried 3 and 1 layer, and each, so the kind of 2 seems to be somewhat locally optimal setup. We use performance, we use layer 1, that's what Maxim tried. It seems that it's not necessary to have the adaptation layer kind of in this spot. Other people have tried just taking these 4,000 dimensional vectors and then feeding them to an SVM, like Rosgirshik I think tried that, and it works also. So I think somehow the representation, the power of the representation is somewhat independent of the classifier which we have obtained.
There is not any lag propagation. You don't change any weights in the future.
Well, once it's trained, so initially, there's a question here. For objects, this is fixed. For actions, we do adapt, not only learn this, but also adapt, fine-tune the parameters here.
You initialize.
So we just initialize with the learn weights for actions, and then fine-tune. It gives a little bit of extra performance. Others have tried, found that, like Rosgirshik have found that fine-tuning, you can just use initialization, fine-tuning helps.
How big is the improvement?
In our case, it's not much. I think it's about 1%. I have it in the tables. 1.5. I think Ross has found bigger improvement.
Even for the action?
Well, we did not find consistent improvements for objects. We did find improvement for actions.
Okay, last question.
I think in your paper you have the overlap when you're creating the training and testing. You overlap between the windows. Why do you have the overlap?
Well, so I think to answer this, I have one slide which I skipped. Is this one? It is. You can think of this really as we converting the Pascal problem into the ImageNet problem. So we would like, as in the ImageNet, we would like to have one most centered object in the image. Yeah. So you kind of, if you move, then you would get the person out of the middle of the image. So kind of the idea is to try multiple different windows so you can really get the person in the middle of the image. So kind of slide it at test time. At training, so this is illustrating the training, we also want to have in the training, like in the Pascal, have the one object centered in the image. If the object is too small, we say it's a background patch. If there are two objects, at the moment the cost function which is using the cross entropy cannot cope with multiple objects. It assumes you have a single centered object in the image. We are working on dealing with this too, but at the moment, single object per image. Yes.
So when you were doing like the back preparation to the initial layers to do the fine tuning, so the training time for that, how much was that? Like from 1 week it goes to...
Right, so for to train this is 1 week.
Yes.
Then training this is about a day. For the fine tuning, I don't know. This I actually have to ask Maxim how long does it take. But I would assume it's less than a week, but I don't have a concrete number yet.
And you were using one GPU or two?
One. So the network is the same style as the architecture as Josef, but on a single GPU.
Okay, we need to stop here.